Okay, Assalamualaikum warahmatullahi wabarakatuh. This is a tutorial for Chapter 7, Entropy, Thermodynamics. Let's go to the first question, 7.56. A piston cylinder device, contain 5 kilogram of steam. Mass is 5 kilogram and the substance is steam. The initial temperature is 100 degrees Celsius with a quality of 50%. So you know already the location by knowing, given the quality, you know that it is already in the, the state 1 is in the saturated mixture, liquid vapor mixture. Okay, you are given the initial temperature. And then this steam undergoes two processes. The first one, 1 to 2, heat is transferred to the steam in a reversible manner. Okay, so that is a keyword there as well. Heat is transferred, so you have Q into the system, while the temperature is held constant. So temperature is constant until the steam exit as saturated vapor. Okay, so we know that heat is added. Initially, the quality is 0.5, x equals to 0.5. Then we add heat to the system until the all steam becomes saturated vapor. So I believe you can describe it in the diagram. Okay. And then 2 to 3, the steam expands in an adiabatic. Okay, adiabatic. Remember, no heat transfer, adiabatic, and still in reversible process. Okay, until the pressure is 15 kilopascal. Okay, so generally, I think we can understand the process. Okay, the processes 1 to 2 and 2 to 3. Okay, the first question is to sketch the processes with respect to the saturation line on a single TS diagram. Okay, let's try on that part. So, okay, the first question, let's draw the TS diagram. So we know that it is steam and we have this saturated condition. So let's have our saturated line. Okay, this is T and S diagram. Okay, initial condition, we know that temperature is 100 and X equals to 50%. So let's just take this as 100 degrees Celsius. Let me try to change color there. So that will be easier for us to visualize. Okay, let's see. This is 100 degree temperature line. So we know that the state 1, the initial state is at that point, somewhere there. So we can label that as state 1 because temperature is 100 degree and quality is 50%. So 50% vapor and 50 saturated vapor and 50% saturated liquid. Okay, heat is transferred to the steam, irreversible, we'll get to that. Okay, while the temperature is held constant, so you know the temperature will remain constant until the steam exists as saturated vapor. So you know that it will undergo this process or this path until it becomes saturated vapor. All the steam become saturated vapor. I think that will be quite straightforward. Okay, constant line, and we would expect, remember, the saturated condition, you have constant temperature and constant pressure. We can check in the table a bit after this. Okay, all right. So, okay, then we can go to the next stage. The steam expand adiabatically, meaning that there is no more heat transfer. We know that heat is transferring into the system during this 1 to 2. Reversible process, okay, reversible process, but no Q. Okay, Q is equals to 0, but reversible. So there is this is a closed system, so you would expect it to be isen. This is isentropic condition. Okay, which means that S3 is actually equals to S2 by this condition. Adiabatic, no heat transfer. Closed system, no mass transfer. So entropy cannot transfer through heat or through mass flow. And then we have a reversible process. So there is no S generation. All right, so we know that it will be vertical, 2 to 3, but we are not sure up or down. Okay, let's check in terms of the pressure. Let's draw this constant pressure line. This is constant pressure. You would expect it to go something like this. This is the P. Let's call, well, let's just call P1 for now. Okay, and we can check from our table. Okay, if we go to table, this is a steam, so it should be A4 table with temperature. Okay, this is our A4 table. Temperature 100 degree, we know that saturated pressure is 101.42. So this is a constant pressure line of 101. Oops. We go back here. Okay, 101.42 kilopascal. Okay. All right. And then we mentioned here, it dropped to, it goes to 15, which is, it will drop since initially it's 101, then down to 15. And we know that the lower pressure should be in the bottom. So let's say that this is our P equals to 15 kilopascal. And if we draw line, okay, something like that. So we would expect then the process from 2 to 3 will go this way, then vertical down until you reach this point. Okay, it is isentropic, so S will be constant. That will be the S value where S2 and S3 aligns. Okay, and what else? Okay, I believe that would be all for part A, right? Okay, all right. Okay, for B and C, let's check. For B, heat transfer to the steam in process 1 to 2. We know that from 1 to 2, this is where heat is transferring in. Let me just describe. This is Q in. 2 to 3, there is no heat transfer in or out, but expanding, okay, we would expect we're going to have a work out from the system. Okay, this 2 to 3 will give you the work out. And also it mentioned here, part C is the work done, okay, by the steam or work out in that case. Okay, B, steam process, heat transfer to the steam process. We know that Q in this case is nothing but, this is Q in, which is nothing but Q 1 to 2 in terms of the process, if you want to just indicate the direction. Okay, and we know that it will be simply given the mass H2 minus H1, okay, that would give you the heat transfer to the system. Why H? Why not U? Because we have a piston cylinder, we would expect as we add on the Q, then having pressure constant, we are expecting the piston to rise, okay? So the volume will increase. So we're going to have the boundary work there. Okay. What about the C? C work done or work out. Okay, work done by the process. Okay, this is nothing but W2 to 3, and we know that the value would be, you can calculate the value, it would be U3 minus U2. And in fact, we would expect 2 is larger than 3 since our energy is leaving the system. Okay. All right. Why instead of H, now we are using U? Okay, we mentioned there the process steam expand in adiabatic reversible process until the pressure. Now the pressure changes, meaning that the piston will remain constant. Okay, the volume doesn't change in this case, so the pressure will increase, right? Okay, so having H and U here, we need to solve the problem. Now we need to go to each and every state to get all the properties. Okay, so at 1, let's check at state 1. State 1, what we are given is T1 equals to 100 degrees Celsius and X is equals to 0.5. So if you refer to the table, let me just go to the table quickly. Okay, for 100, okay, information we need here is H value from the equation that we have seen earlier. Okay, we are given X equals to 0.5, so you need the HF and HFG, which is 419.17 and 2256.4. Okay, so going back here, so you know that H1 is nothing but HF plus X HFG. Okay, from the table, you know that HF is 419.17 plus X is 0.5 given from the problem, and HFG was 2256.4. Okay, so if you calculate this, then you will get H1 to be equals to 1547.4 kilojoule per kilogram, right? Okay, this is the only thing that we know. Sorry, this is the only property that we need for at state 1. Okay, now we can go to state 2. Okay, we know that T2 is equals to T1, 100 degrees Celsius still. And we know also the quality now is equals to 1. It is already fully vaporized. Okay. So again, go to the table. Then we do not need to, what we call that, find the saturated liquid. We can take from the saturated vapor condition, okay, which is 2675.6 kilojoule per kilogram. Okay, that would help us to solve part B. Basically, we can solve part B already now. H2 and H1 is given. Okay, let's just continue with all the properties since we are using the table now. To get to state 3, okay, we don't have much information. We know at 3, we are given the pressure. P3 is equals to 15 kilopascal. That's the only information we have. But from here, then already we concluded that adiabatic reversible for closed system. So we know that it is isentropic. So S3 equals to S2. Okay. So having this, then we should be able to find the properties at state state 3. So we need at 2, we need to find what will be S2. We know already the 2 properties there, so we can find S2, which is nothing but Sg at that location. If you refer to the table, then it will be 7.3542. 7.3542 kilojoule per kilogram. Okay, that would help us to get information in state 3. And if you refer again to C, then you also need internal energy at 2 for us to solve for C. So let's just get it done there. So U2 is nothing but UG and 2506. If you refer to the table, 2506.0 kilojoule per kilogram. All right, so these are all 3 information we need at 2. Then we can go here now. S3 is equals to 7 This is 7.3542. Okay, that is the information. And pressure is 15 kilopascal. So we are not sure. Well, from the figure, then we know that it is going to be in the saturated mixture. So let's check, okay, in our table whether that is correct. Now we cannot use A4 because you are given the pressure table, pressure information. So you need to go to pressure table A5, A5, yeah. A5, we know the pressure is 15, okay, 15 kilopascal, and we know our entropy, okay, is 3 point, what was it? 7.35 42. 7.3542. If we check in this table, SF is 0.7549. Okay, our entropy is larger than that, which is okay. And then the high side, the maximum saturated vapor is 8.0071, and ours is 7.3542, lower than the saturated vapor. So we are okay. It is correct. It is within that region. So let's go back to our work. So knowing that, then we can use table A5. Okay. Let me just state here, table A5. We have been using table A4 the last time. So from table A5, then we know SF equals to 0.7549. SG equals to 8.0071. Well, we can also find SFG for our calculation, 7.2522. 2522. Okay, and we know that our S 7.3542 lies between this SF and SG. All right, so we can find the quality. Okay, if you find the quality, it turns out to be our S 7.3542 minus 0.7549 divided by SFG, which is 7.2522. Okay, that would give you the value of 0.911, which looks reasonable in our figure also. Okay, 91% of the substance is already in saturated vapor. All right, so we have X. So just a matter of, we need a U3 here to solve our problem. Just a matter of using the same table. U3 is nothing but U F plus X U F G. Okay, if you refer to the same table, table A5, you have UF equals to 2 to 5.93. Okay, we have our X 0.911, and then UFG from the table is 2.1. You can refer to the table. Okay, so if you solve this, then you know that your U3 is 2247.9 kilojoule per kilogram. All right, so we have all the properties needed to solve for B and C. Therefore, you can say that Q12, okay, 12 is nothing but equals to mass. Mass is already given, okay, 5 kilogram. And then H2 is 2675, 2675.6 minus H11547.4 kilojoule per kilogram. So you can eliminate or cancel the kilogram. If you solve this, then your Q turns out to be 5641 kilojoule or 1 kilojoule. Okay, 5641 kilojoule. That will be the first answer, which is for B. And then the second one, W out, okay, or W 2 to 3, okay, it's nothing but 5 kilogram, okay, U3, which is 2247, minus U2, 2506, 2506.0 kilojoule per kilogram. Again, cancel that, and work turns out to be, of course, as we expected, it will become negative because you lost your internal energy, okay, due to the work leaving the system, 1291 kilojoule. Okay. All right. You can keep that negative, or otherwise, then you can just restate kilojoule. Okay. Work to 3, which is indicating a work leaving the energy leaving the system. All right. That will be the answer for this problem. Let's go to the next problem. 760. Okay, a 50 kilogram copper block initially at 150 degrees Celsius. So you know the copper initially having that 140 degrees Celsius, drop into an insulated tank. Okay, important note that contain 90 liter of water. Okay, we have water and the temperature is 10 degrees Celsius. We would expect, since the temperature of the copper is a lot higher than the water temperature, then the temperature of the copper will drop and the heat from the copper will be transferred to the water, so the temperature of the water will increase. So the question is to determine the final equilibrium temperature and the total entropy change for this process. Okay, final equilibrium temperature, meaning that there will be a time in which the temperature of both copper and water will eventually become the same, so no more heat transfer going on. As long as copper temperature is still higher, then there will be heat transfer leaving the system. So you know that you want to find the final point in which the two temperature of the water and the temperature of the copper will be the same. And the total entropy change for this process, that will be the S generated due to the process. Okay. All right. We can make some assumption here. Okay. Of course, incompressible for liquid and solid. Okay. Compressible. Then we can use our the equation that we went through in class. Okay. Also, we can take assume the specific heat at room temperature. Specific heat at room temperature. Okay. That would help us a lot. Then we can just simply use the table. Okay. And then, of course, the problem is already indicated there, well insulated. So Q equals to 0. When we define okay, let me describe. Let's say that this is our tank. Copper is inside, and we have also H2O, water, and then we have copper there. So if we define this as our boundary between the tank and the surrounding, we can say that Q is equals to 0 there. Insulated, no heat transfer out of the tank, but heat will be transferring from copper to water inside the tank. Okay, heat transfer inside is going on, but not outside. So we assume Q well insulated, so no heat transfer outside. Okay, and of course we can assume there is no other energy due to the potential energy change or kinetic energy. Okay, so from this, then first we can refer, or we can find the property of the substance or the material from table A3. Okay, based on our assumption there, then we can go to this table to get the property. Let's go to the table. Table A3. Okay, this is for solid. Okay, you'll be able to get the Cp and density. Let's start with the liquid. Okay, this is property of common liquid. We are interested in water. Okay, and from this table, then you are given for various temperatures. So since we assume to be room, then we can take around 25 degree Celsius. So the density is 997 and the specific heat is 4.18. So we will be taking that value. For copper, if you check this table, for copper, we have various temperature there, but the room temperature, we can take around 27 degrees Celsius there. So that will be our density and um, specific heat, Cp. Okay. All right. We do not need the density because we are given already the mass of copper. We need for water since we are not given the total mass. So we need to do some conversion. Okay, let's go back to our problem. So from this table, then we can say water. Okay, we take it at 25 degrees Celsius. So rho is equals to 997 kilogram per meter cube. And then specific heat at that temperature is 4.18 kilojoule per kilogram degree Celsius or Kelvin. Okay. And then copper, for copper at 27 degrees Celsius, that's the only information we have in the table. So specific heat for copper, let me just put the subscript there just to indicate so that we will not mix up. 0.386 kilojoule per kilogram degree Celsius or Kelvin. Doesn't matter because delta T, then you can just, you do not need to convert to Kelvin. Okay, so how to find the final temperature? Assuming that there is no heat transfer out, so we can find the energy balance in the system or in the tank. So energy balance, we know that this is the general energy in minus energy out should be equals to the change of energy in the system. Okay. Focusing on the inside the tank, energy in, well, as our boundary there, okay. If we focus on the energy on the boundary, energy in, there is no energy going into the system, no energy going out from the system, since Q is 0 and this is what we call that closed system. So we know that this will be 0 minus 0 should be equals to the change in the of energy in the system. Inside here, there is a change in the energy due to the what we call that copper and water there. Okay, so let's just take that as this equation delta U. And we can expand delta U here to be more specific for the two substance. Okay, let me just bring to the other side. So that is nothing but the change of internal energy of copper plus the change of internal energy of water. Okay, should be equals to 0. Okay. So this change of energy is nothing but the change of energy of this two within the tank. Okay, and if we expand this relation for solid and liquid, then this is nothing but MC. This is for copper. Okay, TU minus T1. Okay, plus MC T2 minus T1 for water. Okay, 60. Okay, should be equals to 0. Let me erase this. I think it's not very clear there. T2 minus T1, and this is for water. Okay, so that will be our energy balance relation. The final temperature we would expect T2, if you are talking about equilibrium there, we want it to be the same value. Okay, before we move, then we need to find M for water. We have M for copper, 50 kilogram. We are given the volume of the water. So let's get the mass for water. So M for water is nothing but rho by volume. Okay, rho already from the table, 997 kilogram per meter cube. Multiply by volume, you have 90 liter. Convert 90 liter, we have 1 meter cube is nothing but 1000 liter. So we can cancel liter there. And mass m cube. No, not mass, meter cube, sorry. Okay, so calculate this, then you get the value to be 89.73 kilogram. Okay, that will be the mass for water. Okay, so we have mass copper, we have mass water, we have specific heat for both copper and water. And of course, we have the initial temperature. So everything is known except T2. Let's just substitute into that relation. Therefore, so let's just put that 50 kilogram multiply by C for copper, Cp for copper, which is C, okay, in this case, 0.386 kilojoule per kilogram Celsius. And then delta T is T2 minus. Copper initially is 140, so 140 degrees C. So you can cancel that, you will end up with kilojoule, but still T2 is unknown there. Okay, plus mass for water is 89.73 kilogram, multiply by Cp for water 4.18 kilojoule per kilogram degree Celsius, and T2 minus T1 for water is 10 degrees Celsius. The unit outside the bracket. And that should be equals to 0. We need to close the bracket as well. Okay, C will cancel, kilogram will also cancel. Okay, so everything is known except T2. So if you solve this relation, then you'll get T2 to be equals to 16.4 degrees Celsius, which is 289.4 Kelvin. Okay, that will be the first question. Okay, so you know eventually then the two will be constant temperature at 16.4. Okay, that is the first part. The second part, total entropy change. As we can see, as we can say earlier, then this is the entropy generated. So what we can do is to find the change of entropy for both copper and water, and the excess will be the entropy generated. So we can find delta S for copper, which is nothing but this is the equation that we have, okay, for constant specific heat, T2 over T1. Okay, everything is known. We have 50 kilogram. Cp is 0.386 kilojoule per kilogram. You can say Kelvin, okay, or Celsius, since we are using, it doesn't really matter. Okay. Okay. As mentioned in class, you can use that interchangeably, so long that it is a delta T relation there. Okay. or ratio in this case. And then we have natural log of 289.4 divided by 413. Okay. All right. So if you solve for this, you will get minus 6.84. 6.864. Okay. Minus 6.864 kilojoule per Kelvin. Okay. All right. And then the other one for water, again, same equation. So you're going to have 89.73 kilogram multiplied by 4.18 kilojoule per kilogram Kelvin. And then natural log of final is the same, 289.4 divided by initial 10 degrees Celsius, which is 283. Okay, so if you calculate that, you will get 8.388 kilojoule per Kelvin. Okay, therefore the entropy generated for Sgen is equals to total entropy change, okay, which is change of entropy of copper plus change of entropy for water, which is minus 6.864 plus 8.388. So if you solve that, you will get 1.52 kilojoule. So this will be the final answer. The entropy generation in the amount of 1.52 kilojoule Kelvin. Okay, and we know that Sgen will only be either 0 for reversible process or positive for irreversible process. So in this case, then it is an irreversible process. Okay, I think we'll stop there for these two problems. We'll continue with other problem next time. Okay, thank you. Assalamualaikum.